I'll get right into it then. My name is Zollner, and I'll be talking about the combustion of monomethyl-hydrazine and nitrogen dioxide. So monomethyl-hydrazine and nitrogen dioxide have been used as rocket fuels. It's a very exergonic reaction, creates lots of heat. The goal of this research is to look at the activation energy and the barrier. And my hypothesis at the start of the project or research is that the activation energy will have to be higher than the barrier. And then here is the reaction. So some various methods. The Arrhenius equation. This is just the Arrhenius equation solved for the activation energy. This is the equation we use to find the rate constant in the MATLAB. The Hamiltonian, the evolution operator, wave function, and the probability of the product and the probability of the reactants. So methods continued. In this experiment, we changed the initial momentum of P naught. And as you do that, it also changes the value of the temperature, as seen here. The simulation was ran for 24 femtoseconds, and one thing to note is the proton is quantumized. So this was the kind of video player of the research. So the red and blue line represents the quantumized proton. However, the red line is offset, and that's why it's higher, so it represents kinetic energy. The green line represents the barrier. Here, the x-axis is reaction coordinate, and the y-axis is the potential energy surface. One thing to note, as the wave packet met the barrier, you could kind of see a little bits going through the barrier, indicating that proton tunneling is occurring. So here's just a better look at the barrier. The barrier energy was 0.551 electron volts and had a height of 0.119. So here is the line regression plot of the Arrhenius equation. The dotted line is the best fit line, and the solid blue line is the plotted points. In the upper right corner is the best fit line equation. And to go from the best fit line equation to activation energy, one multiplies it, the AX of the Y equals AX plus B by the Boltzmann constant. And for this project, I used the Boltzmann constant of 8.16 times 10 to the negative 5 electron volts per Kelvin. And with the line regression plot, I got a value of 1.566 times 10 to the negative 5 electron volts per mole using the line regression model. And just using the Arrhenius equation, plugging in a P naught value of 2 and 1, I got a value of 6.783 times 10 to the negative 5 electron volts per mole. And you can see that equation here. So this proved my hypothesis wrong, that the activation energy does not have to overcome the barrier, and it can be much, much lower than the barrier. So here's just a couple different graphs. The P naught 1, 2.5, and 5, where the difference is, as one can see, is the amount or probability on the left gets smaller and smaller and shorter, and then the probability of the electron on the right gets bigger and bigger, indicating that more protons go through the barriers. And then here I have just a position versus time plot, where position is on the x-axis and time on the y-axis. And just something neat I thought is that as P naught increases, and P naught should be 1 instead of 0, that's a typo, 2.5 and 5 are going across respectively, where as P naught increases, kind of the width or the angle as it kind of comes out decreases. I just thought that was kind of neat and wanted to include it. So before I take questions, I'd like to thank Dr. Killen and Dr. Hahn in helping me with this research. Any questions?
Please join me in thanking Jared.